Greetings and welcome, internet friends. Mr. Waddy here, and today we're going to be talking about solids, three-dimensional figures of a variety of sorts. We're going to be classifying them, giving them names, and talking about some of the components they have. And later on in this chapter, we'll end up dealing with things such as calculating the volume of solids or maybe the surface area of a particular solid. And so, the first kind of solids we're going to deal with today are going to be polyhedron, which not all of the objects you see on the screen right now are polyhedron. The ones that are composed up of polygons are polyhedron. So things like a cube or a box, which we'll call a rectangular prism. This is a polyhedron. This is a triangular prism. And this pyramid is a polyhedron. But figures or objects, rather, that have smooth surfaces, or even a circular face, which isn't a polygon, even though, yes, I realize that this software is estimating a circle by having a number of sides around that object. Those are not going to be polyhedron, but they still are solids. And so I've got a foldable note for you that's going to fold kind of like a bureau. And on the outside, it's going to have a variety of images that kind of look like this. And we're going to go through and classify these things, name them, and talk about some of their components. And so nothing too crazy. We're just going to have this so that we know some of the terminology that is going on here. And so here we go. First of all, polyhedron is a solid three-dimensional object that is bounded by, it's closed by polygons. They're called faces. And an edge of a polyhedron is a line segment. So let's see. So a face would be something like this right here is a face. An edge of a polyhedron is a line segment. And so you can see here's an edge. So each of these faces is made up of multiple edges. They're like the side of a polygon. And then a vertex of a polyhedron is a point where three or more edges meet. And so these polyhedron have a number of vertices, which is the plural of vertex. And speaking of plural, it says the plural of polyhedron is polyhedra or polyhedrons. All right, so let's talk about names of some of these things. And so the first three objects that you see here are all in the same family. And there's a particular theme that is related to these objects. They are going to be types of prisms. And so this is going to be a prism, this is going to be a prism, and this one is going to be a prism as well. And the type of prism, well, actually, first I'll specify this. A prism is going to have two faces. Oh, I think I was doing purple. Two faces that you could perceive as being the top and bottom of it. We'll call those faces bases. And the prism is going to be named based on the shape of its base. And so this one we could call a rectangular or square prism. It's difficult to know what that shape happens to be. This one, it has two bases that are triangles. And so this one is going to be a triangular. And repeating myself is such a Khan Academy thing to do. Triangular prism. This one will be we'll call it a rectangular. Right, the classic box shape. In the case of a rectangular prism, if all of the faces are squares, then it's called a cube. Right, we've seen those before. And this one, its bases, the faces that are the bases, are pentagons. And so it's a little bit weird to use the word pentagon as a descriptor, an adjective. So we call this a pentagonal. I think is the way to pronounce it, but you could call it a pentagonal prism, but pentagonal sounds way cool in my mind. So a pentagonal prism, and you could imagine that I could increase the number of sides for the base. I could have an octagonal prism, all sorts of things. And so those are the names of these three figures. A prism is a three-dimensional polyhedron that has two parallel bases. And then the sides of that object are made up of, they're going to be quadrilaterals. So notice here's a triangular prism, and all of the side surfaces are rectangular. Right here, all of the sides are rectangular. Those are the only two prisms that I have here. Sketch. So let's extend this. So first of all, is this a polyhedron? Is it made up of polygons for its faces? And yes, this. And in fact, all three of these are going to be polyhedron. Yes. But now let's count the number of faces. All right, so this one's got 1, 2 for the top and bottom, and then 1, 2, 3 for the side. So that's a total of 5 faces. This one has top and bottom, 2 sides, a front and a back. That's 6. I mean, if you think about a cube is a 6-sided die, so that would make sense. And this one's got the 1, 2, top and bottom. And since this is a pentagon for its base, I know that it's got 5 edges, so it must have 5 lateral surfaces that extend from it. So that's going to have 5 that go around and 1, 2 on top and bottom. Happens to be 7 for the number of faces. Now the number of edges is a little bit trickier to calculate. So the number of edges, so each base has 3. 1, 2, 3. That's 6. And then this one has 3 connecting the vertices of those bases. So it looks like 9 edges here. So this one has got 4 on top and bottom, so that's a total of 8. And then 4 extending down from each corner, so 8 plus another 4 is 12. Number of edges. And this one's got 5 for each base. That's 5 times 2 is 10. And then 5 extending down, so another 5 is 15. Number of edges. So that's faces and edges. Let's see if we can figure out vertices here. Be a little bit trickier. So each base has 3. 1, 2, 3. 1, 2, 3. And that's actually got all of them, right? The lateral faces already had their vertices counted. So that's a total of 6 vertices there. This one, each base has 4, and that's going to count all of them, so that's a total of 8. Right, so we're just practicing some of the terminology, writing down these facts for our foldable, getting used to the name. A prism, once again, has 2 parallel bases, surfaces, parallel. This one's got 5 and 5, so that's going to be a total of 10. All right, so those are the idea of prisms. Prisms are polyhedron, right? Yes. And there's actually going to be a relationship between the number of faces, edges, and vertices. I might end up leaving that aside for now to see if you can figure out the relationship between the number of faces, edges, and vertices that will be true, a formula essentially, that will be true regardless of the polyhedron. So let's keep going. Now, the next figure, you can see kind of, does have 2 bases, except the bases are not polygons, right? They're circles, not a polygon. And so this one's not a polyhedron. You're probably familiar with the name of this solid. This has got its own specific name. It's called a cylinder, right? And a cylinder is not a polyhedron. And since it's not a polyhedron, it doesn't really have any faces to it because faces are polygons. Circle's not a polygon. Whatever this lateral surface is, that's not a polygon, but we would call it a surface. We also don't necessarily have any edges in the proper sense of the term because edges are segments. And right, you could imagine this kind of has like 2-ish if you were to extend the meaning of the word. And this one has no vertices, so these ones are all just blank. So that's a cylinder, and since it has these 2 bases that are kind of parallel planes to each other, the formula for the volume of these objects is going to end up being somewhat similar. but we're not going to worry about formulas for now. Let's see, here's another figure that hopefully you can immediately recognize is not a polyhedron. It has no bases to it. It's got no faces, but you probably are familiar with this. This is called a sphere, right, which is a ball-type shape, right? And actually, I think I've got, we've got a little sphere right there, little sphere object. I also have kind of an elliptically rotated object right here. This is called an ellipsoid, which is not a sphere. You can imagine a football shape is kind of like an ellipsoid. And then this one looks like it's just an egg. I don't know a great way to mathematically describe that for you. But yeah, so we've got all sorts of these little relationships there. But a sphere is really tricky. To draw it, what I usually do is I draw kind of an oval, and I might draw another oval like this. Notice the front one edge of the oval is solid, the other's dashed, so I'm imagining that these are behind the sphere. These are in the front, and I kind of just draw these two ovals inside of a circle. I would imagine that there's a center to the sphere. You could perceive that there is a radius, right, that a sphere contains. And that radius is actually going to be true in all directions. All of those are the same. And in fact, the definition of a sphere is very similar to the definition of a circle. A circle is the set of all points equidistant from a center in 2 dimensions, while as a sphere is the set of all points equidistant from a center in 3 dimensions. And so a sphere doesn't have any faces, edges, or vertices. It is not a polyhedron. Okay. Here we got these next 3 objects are in the same family. You'll notice that all of them, if I think of it this way, have a single base. So instead of 2 faces that are parallel, they all have a single base to them and a vertex that is off of that base that the remaining edges connect to. And so these objects, perhaps you're familiar with a name for them. They are called pyramids. So pyramid. Nope. Oh, I swapped what side the name is on. Brr. So pyramid. So all of those are in the pyramid family. Nope. Spell it right. And pyramids are going to have similar formulas when we calculate their volume. Kind of similar formulas for surface area as well. We'll talk more about that in future chapters. We're just talking about names today. Do you think these... So the pyramid, has a single base and a vertex that every other edge kind of connects to. They are a polyhedron, yes. Because all of those, we could imagine... so for this pyramid, all of its faces are made up of polygons. And a pyramid, besides knowing that it's got a base and a vertex at the top, we name the pyramid based off of the shape of its base. And so this object here looks like it would be a square pyramid. We'll call that. Yeah, we'll call this one a square. Maybe it's not square, but it could be a rectangular pyramid, something like that. This one, because it's got a triangular base, is a triangular pyramid. And this one would be a, once again, the cool word, pentagonal or pentagonal pyramid. And so these are all in the same family of pyramid, a single base, not 2 parallel bases. They do have lateral kind of faces to them as well. But let's count the number of faces. So let's go up here. So this one's got 1 base, and then it would have 1, 2, 3 sides. That's a total of 4 faces. 4-sided die is going to be a triangular pyramid. I've got some on my desk you guys could check out. A square pyramid, so that's 1 face there, and then 4 lateral faces that must extend off of each edge and then meet at the vertex. And so it's kind of the base plus the number of sides that the base has would give me the number of faces. So that's a total of 5. And for this one, 1 base and then 5 faces that extend off of the bottom. And so that's going to be 5 plus 1 is 6 for the number of faces. Oh yeah, this one, yes, is a polyhedron. All of its faces are polygons. The number of edges, let's see if I can find a way to quickly count some of these up. So I've got 3, 1, 2, 3, and then one more edge per corner of the base. So 3 plus 3 is 6. So this one's 1, 2, 3, 4, and then one more edge extending from each of those corners. So 4 plus 4 is 8. Yep. And this one has 5 on the bottom. And by the way I would draw this, which if you ever needed to, I typically draw the base first. I then draw the vertex up above it. Usually it's up above the center of it, of the base. And then I just connect the dots for all 3 of those edges, or 5. So let's see, 5 edges on the base plus 5 is 10. See if I can quickly count these vertices. So I've got 1, 2, 3 on the base, triangle, and then 1 on top. So it looks like to count the number of vertices in a pyramid, you just count the number of the base and then add 1, because there's always that one vertex that has risen up above the plane of the base. So this one's got 4. 4 plus 1 is 5. And this one's got 5 on the bottom and 5 plus the 1 on the top, 6. And so for all of these polyhedron, there is a relationship between faces, edges, and vertices. Maybe as a challenge for you to consider. See if you could look at those numbers and see if for all of them, is there a relationship? Is there a pattern that you could derive that if I knew 2 of these facts, that I could always get the third? And that would be true for any 2, right? The convenience of a formula is that it does that. So these are pyramids, right? Pyramids are named by the base. And let's see, here's another object which is kind of it's similar, right? I've got a single quote-unquote base, except it's a circle, it's not a polygon, and then a common vertex, and then the infinitely many points around that circle all right, swoop up towards that common vertex. Perhaps you know the name of this as a cone. And a cone is not a polyhedron because, one, the base that it has is a circle, which is not a polygon, and this lateral surface that wraps around it is kind of a weird, right, surface. We'll actually analyze that a little bit more when we talk about the surface area. Kind of tricky to perceive. And it has, therefore, no faces, edges, or vertices since it's not in the polyhedron family. But it's going to have a similar volume formula to the pyramids, right? So you actually can see there's a bit of a similarity between them. They have a single base and a vertex that everything else extends towards. And let's see, here's another object. This one's kind of like a sphere. That's the last one in our packet, right? This is called a hemisphere. Right, and so perhaps if you know your geography, you're familiar with it, right? Northern and southern and western and eastern hemispheres. So it's got a circular base, but it's the easier way to kind of think about it is just a sphere that was Fruit Ninja sliced in half, and it is not a polyhedron, but it's got like kind of this surface, right? That extends right around, wraps around like so. You get the idea. Hemisphere. Do I have a hemisphere on this? No, I don't. I just got the regular sphere. But you can imagine if I slice that sphere at the equator, that's what we would end up getting. And so here's a series of kind of interesting solids, right? We've practiced classifying them, whether they're prisms or pyramids or kind of these non-polyhedron objects. But these aren't the only types of solids. We actually have a special set of them, which are here. And these are called the Platonic solids. And so here we have a tetrahedron, the triangular pyramid. Here's an octahedron, which is kind of like 2 square pyramids connected. Right? There's a cube. This is an icosahedron, a 20-sided solid, and here's a dodecahedron, which is a 12-sided solid. And so these are called Platonic solids, right, named after Plato, and there's only 5 of them. There will only ever be 5 Platonic solids, at least in 3-dimensional space. If you end up going to 4 dimensions, there's some interesting that happen. Maybe a video about that at some point. But the Platonic solids have a special feature in common. Not sure if you can tell what it is. It's that every one of their faces is congruent every other face. So all of these triangular faces in a tetrahedron are congruent to the others. All of the triangular faces in the octahedron, 8-sided, are congruent to each other. A hexahedron, right? We just call that a cube, I suppose. Right? All of its 6 faces are congruent. The 20-sided icosahedron, all of those triangles are congruent faces to each other, and these pentagons are all congruent to each other in the world of the dodecagon. Oh, man, I almost said dodecagon. Blah. Dodecahedron. Yes. And so, yeah, so those are just kind of some special cases to be aware of. And in the tetrahedron, one of the ways that maybe you've heard of that term before, I don't know if, I know some of you are, right, firefighters, or if you've ever had to put out a fire and wondered how, there's what's called the fire tetrahedron, which is a 4-sided pyramid. You can imagine all of these faces kind of coming together. And these are the 4 things that must exist in order for fire to happen. They used to, back in the day, have just the fire triangle, which was made up of heat, fuel, and oxygen, right? Those 3 components, they used to say, are the 3 things that needed to exist. But they've since added a 4th and now moved into the 3 dimensions, having the, right, fire tetrahedron. And the idea is this, that a fire needs all 4 of these things to exist. So if you want to put a fire out, you just have to remove one of them. So for instance, water, see, oh, there's a little water guy. I don't know. Water being put on a fire reduces the temperature, the heat, and if I knock out one of these faces, the fire will go out. Water is also used to deal with the oxygen that's feeding a fire, where if you create a mist, it'll change the kind of fuel to air ratio, and it won't be able to burn. Or you can imagine, like, putting a jar over a candle, right, closing it in. Eventually it burns up and consumes all the oxygen and then can't continue, even though it might still have had fuel. Fuel can be removed from a fire. You might be like, Mr. Watt, you're completely distracted. Yes, I am, I realize, but hey, it's kind of an interesting fact. Fuel can be removed from a fire if you either right, reduce the fuel source by, right, shutting it off if it was like oil. If it's a forest fire, right, you could rake out a perimeter boundary that then once it reaches that boundary, it has no fuel to burn and will go out. You could also pre-burn a boundary, something like that. And then, like, chemical reactions, those are like if you have an electrical fire, oil-based fire, you might have a particular fire extinguisher that reacts chemically to disengage fire. So that's some interesting language. Here's a challenge problem that I want you to think about. I'm hoping to 3D print this for us in a moment, but this is what I want us to think about for a minute. Kind of a challenge. So imagine this object. Actually, I've got it right here. Ooh, oh, that's actually like pretty lined up. So here's this object, and kind of like that kid's game of like square peg through the square hole sort of thing. This one's technically not a square, a rectangle, but that's fine. But I want you to think about what solids could perfectly pass through, where at one point it's touching all of those edges, could perfectly pass through a square hole, right? Which of our solids could perfectly pass through a square hole? So think about these objects, right? And you might be like, oh, right, like if I had a cube, it could pass through a square hole. Or a square prism, right? Even if one of these bases was way higher, as long as the square base matched the square hole, you could still just pass it through that 3-dimensional object right there, and it would just take more time. Are there others that could pass through? Well, I think actually a square pyramid, right? If the square base matches, you could pass it through perfectly through that opening. Right, so you could kind of imagine that being the case. I don't think I could have any of the other solids pass through it. No, not quite, not quite. How about a triangle here? What solid objects could pass through a triangular hole? Think about that. Well, triangular prism would work, right? If the triangular base matched. Maybe a triangular pyramid, right? Could pass through if the triangular base matched. This one's actually an interesting question. Could a square pyramid pass through a triangular hole perfectly, where it would actually meet every edge? I'll let you guys ponder that one for a little. Maybe ask me later or in the comments below if you think you have an answer to that. Are there any other objects that could pass through a triangular hole? Actually, this is interesting right here. Maybe I can pull this up. The cone, if I could actually get it straight shot, you could imagine the cone, if I pass it through perfectly, from one perspective, is actually a triangle. And if this vertex was further down, you could imagine it being an equilateral triangle even. So it is actually possible for a cone to pass through that hole and perfectly touch all three edges. And so what I want you to do is think about this sort of relationship here. See, I'm off center now. Here we go. Think about what could pass through the circular hole perfectly. And then this is the challenge question right here. Okay, because maybe so far you're like, Mr. Waddy, this isn't all that interesting. Here's my question. What solid object, which by the way is not going to be any from our list, what would the solid object look like that could pass through all three of those holes perfectly? Perfectly. Right? What would that object look like if it could pass through all three of those holes perfectly? That maybe some rotation or orientation of the object that it could pass through all three. So give that a thought. I think hit everything I need for now. There are some more practice problems in our packet and another lesson video that you can investigate. But thanks for watching, internet friends. Have a great day. Bye-bye.